Good evening everyone, good evening. I welcome you all again to VJEE Enthuse. Hoping that you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone, yeah? Hello Kumar, hello Deborah, hi Surya, hello Farhan, hello Likhit. Hello Praveshini, welcome everyone, welcome to the session. Just let me know in the chat box if I'm audible and visible. Hello Akash, welcome. Welcome everyone, welcome. Well, I'll be doing the solid state Menti maybe day after tomorrow, yeah? Okay, so just give me the green signal from the chat box so that I'll get to know whether I'm audible and visible to everyone or not, yeah? Perfect guys, perfect. So as you all must be knowing, it is going to be the second session from the chapter Chemical Kinetics, right? In the last session, we discussed some basic things about chemical kinetics, right? We talked about the average rate of reaction, instantaneous rate of reaction. Then we discussed the differential form of rate, if you remember, correct? We did some basic questions on that as well. And in the today's session, what we are going to talk about is, we are going to start this session with something called as law of mass action, which you would have studied in your class 11th equilibrium as well, right? And after law of mass action, we'll be continuing with the rate law. And after rate law, there is something called as molecularity and order of the reaction. Everything will be covered in the tonight's session, okay? So before starting the session, for the ones who do not know me, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here on this VJEE Enthuse channel, yeah? Perfect. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. And do not forget to hit the bell icon so that you get the notification of every single session which will be taking live on this VJEE Enthuse channel, yeah? Hi Shruti, good evening. Hello Surya. Hi VSG, what's up? How are you guys doing? So people, these are the topics which we are going to cover in the tonight's session. We are going to start with something called as law of mass action. Then talking about rate law, elementary and complex reactions, molecularity, order of reaction, everything will be discussed in detail right now, okay? Harros Gamer is new to the channel. Welcome bro, welcome. Perfect. So let's get started. Without wasting a lot of time, let's get started with something called as law of mass action, okay? This is the topic which you would have covered in your class 11th equilibrium as well, yeah? Okay, still, I'm just going to give you the quick overview of this law of mass action, because I'm going to use this law of mass action in this chapter over here, yeah? And people, whatever I'll be writing on the screen, I want all of you to note down every single thing which I'll be noting down on the screen, okay? Yes? So let's get going, let's get started with something called as law of mass action, okay? First of all, this law of mass action, it was given by two scientists, right? It was given by two scientists, Gullberg and Lowe. These were the scientists which gave this concept, which is what we call as law of mass action, right? And first thing, this law of mass action, it is a complete theoretical concept. It does not have any experimental background, okay? The law of mass action which we are going to deal with right now, it's a complete theoretical concept. It does not have any experimental background, right? And as per the law of mass action is concerned, rate of the reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficients. What it exactly means, okay? See guys, first thing which I would like to share with you, what is that? Remember, whenever you'll be given with a balanced chemical equation, any reactant or product that is going to be in aqueous form, that means you'll be given with something AQ written in the brackets, like over here in this reaction. First thing, any reactant or product which is going to be in aqueous form, we are going to take its active mass as its concentration, okay? Whenever I'll be having any reactant or product in aqueous form, its active mass will be taken its concentration. Point number one. Point number two, whenever I'll be having any reactant or product in the gaseous form, whenever in a chemical reaction I'll be having any reactant or product in gaseous form, I'll be taking its active mass as its partial pressure, okay, which is denoted by P. right? Yes, and at the same time for gases, we define concentration as well, okay? So whenever I'll be having any reactant or product in the gaseous form, its active mass will be either taken as pressure or its concentration, right? And at the same time, remember, whenever I'll be having any reactant or product in either liquid state or solid state, pure liquid form or pure solid form, its active mass is taken as unity. Okay, its active mass is basically constant, which is taken to be unity, right? This is something which you should remember first of all before starting this law of mass section. Whenever you'll be having any reactant or product in aqueous form, its active mass is taken as its concentration. Whenever you'll be having any reactant or product in gaseous form, its active mass is taken its partial pressure or its concentration, because for gases we define both the terms, right? Pressure as well as concentration. Similarly, whenever I'll be having any reactant or product in pure liquid form or solid form, its active mass is taken as constant, and that constant is equal to unity, okay? Something which you should know before starting this. Now, in this reaction, how many reactants do we have right now? We have got two reactants, this A and B, okay? As per law of mass section is concerned, rate of this reaction is directly proportional. It is directly proportional to the product of active masses of reactants. I'll say active mass of A raised power the stoichiometric coefficient of A, which is N1, multiplied by active mass of B raised power its stoichiometric coefficient, that is N2. Yeah. As per your law of mass section is concerned, rate of reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficients. Okay. Yeah. Now people, as I told you, whenever I'll be having any reactant in aqueous form, its active mass is taken as its concentration. So I can simply say rate of reaction is directly proportional to, instead of active mass of A. A is in aqueous form, so I'll be writing concentration of A raised by the stoichiometric coefficient N1 multiplied by active mass of B. It's going to be concentration of B raised by its stoichiometric coefficient, that is N2. This is how we write the law of mass section. This is how we calculate the rate of the reaction as per law of mass section. And remember one important thing, whatever rate of reaction value you'll be getting from this equation, that rate of reaction is something which we call as theoretical rate. Okay. Whenever I'll be calculating the rate of reaction by using law of mass section, that rate of reaction is what we call as theoretical rate. Okay. Remember this thing, right? Okay. Again, I'm telling you, whenever I'll be calculating the rate of the reaction by using law of mass section like this, okay, the whatever value of rate comes out to be, that rate is what we call as theoretical rate of the reaction, correct? Okay, for example, I've got some reaction as 2 times A. 2 times A is in aqueous form, plus 3 times B, or let's not keep it as 3 times B, let's keep it as plus B, which is again in aqueous form. It gives products. It gives products. How will I be writing the law of mass section for this reaction? I'll simply say rate of reaction is directly proportional to active mass of A. Since A is in aqueous form, so I'll write concentration of A raised by its stoichiometric coefficient, that's 2, multiplied by concentration of B raised by stoichiometric coefficient of B, that's 1, right? Then you can remove the proportionality sign, there will be a constant. And whatever will be the rate of reaction by solving this term over here, that rate of reaction is what I call as theoretical rate of reaction. Okay. So whenever you use law of mass section and calculate the rate of reaction, that rate of reaction which is calculated by means of law of mass section, that's what I call as theoretical rate of reaction. Point number 1. There is something called as a rate law as well. Okay. What is the difference between the rate law and law of mass section? Remember, this rate law is not the law of mass section. But this rate law which I'm going to talk about, it is based on law of mass section. This rate law, it is based on law of mass section. Yeah? Okay. As per rate law is concerned, rate of the reaction is calculated by using the rate law, which is an experimentally determined quantity. What it means? Have a look properly what I'm going to say. Understand properly. Okay. See guys, I'm given with a balanced chemical equation, right? The stoichiometric coefficient right here is N1, right here is N2. Let's assume this A is in aqueous form, this B is again in aqueous form. Let's assume this, okay? How will I be writing the rate law for this reaction? I'll simply say rate of the reaction is directly proportional to the way I used to write law of mass section. In the same way, I'll be writing rate law as well, yeah? I'll be writing rate of reaction is directly proportional to concentration of A in log mass section. I used to write the power over here as N1, but over here in the rate law, I won't be writing the power as N1, I'll be writing the power as X. Okay. Similarly, multiplied by concentration of B. In log mass section, I used to write N2 as the power, but over here I'll use the power Y. Okay, right? This X and Y, these are the terms which are calculated experimentally basically, right? This X and Y are basically calculated experimentally. These are calculated experimentally, and in the upcoming sessions, I'll show you exactly how this X and Y are calculated basically experimentally, okay? Right? Now people, if I'll remove this proportionality sign, I'll write R is equal to, I'll put a constant K multiplied by concentration of A raised power X multiplied by concentration of B raised power Y, okay? So this is what I call as rate law for this balanced chemical equation, okay? This R stands for rate of reaction, okay, and this K, it stands for the rate constant. K is what we call as the rate constant, right? K is what we call as a rate constant, yeah? This X and Y, these are the two terms which are basically calculated experimentally, okay? And how to calculate these terms, this X and Y experimentally, that's something which I'll be telling you in the upcoming sessions, yeah? Now people, if I need to define the rate constant, K over here, understand how will I be defining it? See. First of all, let's assume the concentration, if the concentration of reactants, that means if the concentration of A is equal to concentration of B and both are equal to 1 molar, let's assume the concentration of A and concentration of B both are equal to 1 molar, I can clearly say rate of reaction will be equal to the rate constant at that time, okay? So I can clearly say rate constant is basically the rate of reaction when the concentration of reactants is taken as unity, as simple as that, okay? Rate constant, it is basically the rate of reaction when the concentration of reactants is taken as unity, as simple as that, okay? Right? Now people, few more things about this rate constant. First thing, this is something which I call as rate law. If I use the stoichiometry coefficients, if I use the powers as N1 and N2, I'll be calling this as the log mass section, but over here I'm using the powers as X and Y, so I'll be calling this as a rate law, okay? Right? Now people, first thing, understand, there are some reactions, okay? Before talking about that, let me tell you, whatever rate of reaction comes out to be from this equation, that's something which we call as experimental rate, experimentally determined rate. Whenever you calculate the rate of reaction by using the rate law, whatever value of rate you'll be getting from here, that's something which I call as experimentally determined rate, okay? Yeah? Now people understand, let's say I've got a reaction, okay? I can calculate rate of reaction either by using log mass section or I can calculate the rate of reaction by using the rate law. If I calculate the rate of reaction by using log mass section, that's what I call as theoretical rate of reaction. If I calculate rate of reaction by using rate law, that's what I call as experimentally determined rate, okay? Yes, there are basically some reactions. There are some reactions in which theoretical rate of reaction is equal to the experimentally determined rate of reaction, and there are some reactions as well in which theoretical rate of reaction is not equal to the experimentally determined rate of reaction, okay? And remember, the reactions in which the theoretically determined rate of reaction is equal to the experimentally determined rate of reaction, for those reactions, the value of X is basically equal to N1 and the value of Y is equal to N2. Okay, remember this thing as well. Okay, basically we have got certain reactions in which the theoretical rate of reaction comes out to be different as that of experimentally determined rate. At that time, we cannot say X is equal to N1 and Y is equal to N2. But there are some reactions in which theoretically determined rate is equal to the experimentally determined rate. So for those reactions, you can clearly say the powers in the rate law are the stoichiometric coefficients, right? Okay. Now people, let's talk about this rate constant over here. How did we define this rate constant? As simple as that. Rate constant is basically the rate of reaction when the concentration of reactants is taken as unity. Point number one. Point number two about this rate constant. Okay, there are certain features about this rate constant. Okay, remember, rate constant, it gives the idea about the speed of the reaction. It gives the idea about the speed with which the reaction takes place. And remember one thing, more the rate constant of the reaction, faster will be the reaction. As simple as that. And similarly, lesser the value of rate constant of the reaction, slower is going to be the reaction. So basically your rate constant, it gives us the idea about the speed with which the reaction takes place, okay? Yeah, more the rate constant of the reaction, faster will be the reaction, less the rate constant of the reaction, slower will be the reaction, okay? And at the same time, remember, every reaction, it has got a particular value of rate constant at a particular temperature, okay? Every reaction has got a fixed rate constant at a fixed temperature, okay? And rate constant for the reaction, it changes on changing the temperature. Now the point is, how rate constant of the reaction changes on changing the temperature. That's something which we have to deal with in this chapter only. There's a topic called as Arrhenius equation. In that Arrhenius equation, you'll clearly get an idea how rate constant of the reaction changes on changing the temperature. Right now, you can just remember one thing. On increasing the temperature of the reaction, the value of rate constant increases. Just remember this. On increasing the temperature of the reaction, the value of rate constant of the reaction increases. Yeah. And people, at the same time, the value of rate constant, it is independent on the concentration of reactants as well. Why is that? Why is the rate constant independent of the concentration of reactants? Because rate constant is only defined when the concentration of reactants is kept unity, right? When the concentration of reactants is kept unity, at that time, whatever will be the rate of the reaction, that's something which I call as a rate constant, yeah? Right? So your rate constant, it does not depend on the initial concentration of reactants, okay? Because rate constant of a reaction is only defined when the concentration of reactant is kept as unity, right? These were some important features about this rate constant, right? Now people, in chemical kinetics, we basically classify reactions into two types. Now from here, the actual stuff starts, okay? As per your chemical kinetics is concerned, we classify reactions into two types. One is called as elementary reaction, one is called as complex reaction. The point is, what is elementary and what is complex? Sudhir, this is the English channel, so I'm not supposed to talk in Hindi. There are some Hindi channels as well of Vedantu. You can go to those channels, right, where teachers talk in Hindi. This channel is particularly for the ones who cannot understand Hindi. Yeah? Okay. So people, as I told you, we have got basically two types of reactions. One is called as elementary reaction, one is called as complex reaction, yeah? Elementary reactions are the ones which are completed in a single step. Elementary reactions are the ones which are completed in a single step, or we call these elementary reactions as simple reactions as well. You can call them as simple reactions as well, right? Whereas complex reactions are the ones which are multi-step reactions, which are basically multi-step reactions. These are not completed in a single step, right? Any reaction which gets completed in a single step, right? That's what you call as elementary reaction, or you can call it as a simple reaction. And any reaction which does not get completed in a single step, which takes place in multi-steps, that reaction is what I call as complex reaction. Okay, now talking about this elementary and complex reaction a bit more in detail. As I told you, the reactions which are completed in a single step, those are what we call as elementary reactions. And remember, law of mass action is truly valid for elementary reactions. Law of mass action is truly valid for elementary reactions. What does that exactly mean? Have a look. Let's say I've got a reaction as A plus B. It gives C. Let's say the stoichiometric coefficient right here is 1. The stoichiometric coefficient right here is 2, for example. Okay. I'm assuming this reaction is taking place in a single step, so it is basically the elementary reaction. I'm assuming the reaction is elementary. The reaction is taking place in a single step, yeah? Okay. Now people understand. I can calculate the rate of this reaction in two ways. Either I'll be using the law of mass action and I'll calculate the rate of reaction, or I'll be using the rate law and calculate the rate of reaction, right? Whenever I'll be using the law of mass action to calculate the rate of reaction, that's something which I call as theoretical rate of reaction. And whenever we use the rate law and calculate the rate of reaction, that's something which I call as experimentally determined rate of reaction. Okay. Now the point is, theoretically determined rate by using law of mass action. It is simply going to be concentration of A raised by the stoichiometric coefficient of A, that's 1, multiplied by concentration of B raised by the stoichiometric coefficient, that's 2, right? This is how we write law of mass action. In case of law of mass action, the powers are always the stoichiometric coefficients. But if I'll be writing the rate law The rate of the reaction, which is calculated by using the rate law, that's something which I call as experimentally determined rate, which will be concentration of A raised power X multiplied by concentration of B raised power Y. But remember, in case of elementary reactions, this X and Y, these are basically the powers of the reactants. Okay, right? What is meant by that? In case of elementary reactions, theoretically determined rate of reaction is always equal to the experimentally determined rate of reaction. That means the value of X over here will be equal to 1, the value of Y over here will be equal to 2. As simple as that, yeah? Okay, remember, in case of elementary reactions, theoretically determined rate is always equal to the experimentally determined rate. Okay, so basically for the elementary reactions, if you write the rate law, the powers are also the stoichiometric coefficients, right? This X will be equal to 1, Y will be equal to 2 over here. Or if I take a general reaction like this, let me make you understand it like this again. See, let's say I've got the reaction as N1A plus N2B, it gives products. Let's assume it's a balanced chemical equation, right? If I'll use the law of mass action, I can calculate a theoretically determined rate, right? It's going to be equal to K multiplied by concentration of A raised power stoichiometric coefficient N1 multiplied by concentration of B raised power stoichiometric coefficient N2, right? This is something which I call as law of mass action because I'm calculating theoretical rate of reaction. Now, if I'll use the rate law, I'll be calculating the experimentally determined rate, right? Which is again going to be concentration of A, but over here I'm not going to directly use the stoichiometric coefficient, I'll use X, right? Multiplied by B, I'll use Y over here. But as I told you, if this reaction is elementary, if this reaction gets completed in a single step, at that time, the theoretically determined rate is equal to the experimentally determined rate, which is only possible if the value of X will be equal to N1 and the value of Y will be simply equal to N2. So what I want you guys to remember right now is, whenever you'll be having an elementary reaction, for the elementary reaction, whatever value of rate comes out to be by using law of mass action, same is the value of rate that comes out to be by using the rate law. Or you can clearly say law of mass action is truly valid for the elementary reactions. As simple as that, okay? Yeah, perfecto. Let's move on and let's talk about something called as complex reactions. The point is, what are complex reactions? As I told you, complex reactions are the ones which are not completed in a single step. These are multi-step reactions, yeah? Complex reactions are basically the multi-step reactions, okay? And the steps which are involved in a complex reactions, they are always elementary in nature. What it means exactly, have a look. Let's say I've got a reaction like this, A plus B, it is getting converted into C, right? This C which is formed over here, let's assume this C again reacts with D, it forms E, correct? If I'll add these two reactions, can I say this C and this C will get cancelled out? So I get a reaction as A plus B plus D, it gives E. If I ask you, is this reaction getting completed in a single step? No way. This reaction is not a single step reaction, right? This is a multi-step reaction. Okay, and multi-step reactions are what we call as complex reactions. So this is basically the complex reaction, okay? This complex reaction, it is getting completed in two steps. This is step number 1, this is step number 2, okay? And whatever steps are involved in the complex reaction, those steps are always elementary in nature. So remember, the first step is going to be elementary, and the second step is again going to be elementary in nature, okay? So remember, from now onwards, it's very, very important. Complex reaction is the one which is a multi-step reaction, okay? Yes, and people, whatever the steps which will be involved in writing the complex reaction, those steps are always elementary in nature, yeah? Remember this thing as well, correct? Now talking about few more interesting things, have a look. We have got certain examples of the complex reactions, yeah? Just give me a second, I'll have some water first. All right. Farhan, I didn't get the update about it yet. I'll let you know when I get the update, okay? Yeah? So right now in the long-term batch, I'm only taking one long-term batch right now. That is some NEET batch, okay? Right? All the other lectures I take directly on YouTube. Yeah, when I'll be allotted a batch for you guys, I'll be letting you know about that, right? Perfect. See guys, understand this as well. See, first of all, this is a reaction which I have. NO plus Br2, it gets converted into NOBr2. This NOBr2, it again reacts with NO, it leads to the formation of NOBr, right? If I'll add these two steps, this is step number 1, this is step number 2. If I add these two steps, this NOBr2 gets cancelled out. So you get NO plus NO, that is 2 times NO, plus Br2 gives what? Gives 2 times NOBr. So this is basically the net reaction, which I'm getting by adding these two steps, right? This is the net reaction which I'm getting by adding these two steps, right? So this is basically the example of the complex reaction. And these are the steps of the complex reaction. And the steps which are involved in the complex reaction, they are always elementary in nature. So this step is an elementary step. This is also the elementary step, right? Okay. One is fast, one is slow. It's given in the question. I mean, it's mentioned, right? Okay. Let's move on. Let's talk about few more interesting things. Now, basically, we are going to enter into the chemical kinetics. Till now, it was all basics, yeah? Now, we are going to enter into the actual chemical kinetics stuff, okay? The name of the topic is molecularity. The point is, how do we define this molecularity? First of all, like your law of mass action, which was a theoretical concept. In the same way, this molecularity, it's again a theoretical concept. It does not have any experimental background. This molecularity is a theoretical concept. It does not have any experimental background at all. Okay. Now, before entering into this molecularity, there is something called as collision theory. There is a theory in this chapter only, which is what we call as collision theory. And collision theory is something which we'll be discussing in the upcoming sessions, right? I just want to use one of the postulate of the collision theory. As per collision theory is concerned, for the reactants to form products, these reactant species, they must collide first. Okay. As per collision theory is concerned, for the formation of products, these reactant species, they must collide first. This is the important conclusion. I mean, this is important assumption of this collision theory. In order to form the products, the reactant species, they have to collide first, right? Now I can define the molecularity. The number of reacting species, which can be atoms, ions, or molecules. The number of reacting species, which can be atoms, ions, or molecules, which collide simultaneously to form the product, is what we call as molecularity of the reaction. Okay? In a reaction, I'll be having the reactants. Now, these reactants can be in the form of atoms, these can be in the form of molecules, these can be in the form of ions, right? Now, the number of reacting species which must collide simultaneously with each other so that product gets formed, those number of reacting species which are colliding simultaneously to form the products is what we call as molecularity of the reaction. For example, 2 reacting species are colliding simultaneously and forming the product. So I'll say molecularity of the reaction is 2, right? Let's assume 3 reactant species are colliding simultaneously and forming the product. That means molecularity of that reaction is 3, right? Okay. Similarly, molecularity of the reaction can be 1 as well. Remember, any reaction with molecularity 1 is what we call as unimolecular reaction. Any reaction with molecularity 2 is what we call as bimolecular reaction. Any molecular with molecularity 3 is what we call as, either you call it as termolecular reaction or you call it as simply trimolecular reaction. Okay. Let's try to analyze this molecularity a bit more in detail over here. Okay. See guys, I'm taking certain examples, right? See, we have got H2 plus I2 giving 2 times HI, yeah? So over here, one molecule of H2 and one molecule of I2, they are colliding simultaneously and leading to the formation of products. So how many reactant species are colliding simultaneously basically? 2 reacting species are colliding simultaneously. So I'll be simply saying molecularity of this reaction is 2 because 2 reactant species are colliding simultaneously and forming the product, yeah? Okay, similarly, let's assume I've got this reaction. 2 reactant species of NO and 1 molecule of O2, 1 molecule of O2, 2 molecules of NO. So 3 molecules in total are colliding simultaneously and forming the product. So I'll clearly say molecularity of this reaction is 3, yeah? Similarly, we have got two molecules of HI, right? Two molecules of HI are colliding simultaneously to form the product. So molecularity of this reaction is again 2. Okay. Now what about the molecularity of the first reaction? On the reactant side, we have got only one molecule. So I'll be considering the collision of this calcium carbonate with the wall of the container, right? Okay. Or this calcium carbonate, it will be vibrating. That vibration of calcium carbonate, okay, that is basically the analogy of the collision which we take over here in this reaction. Yeah. Or you can directly consider the collision of calcium carbonate with the wall of the container in which it is kept, right? So we clearly say its molecularity is 1. Okay. Any reaction with molecularity equal to 1, that's called as unimolecular. Molecularity 2, bimolecular. Molecularity 3, termolecular, right? Okay. There are some important points about this molecularity. Molecularity of the reaction, it can never be 0, it can never be negative, it can never be fractional, okay? It does not have any significance. Molecularity of the reaction can never be 0. What is molecularity basically? The number of reacting species that should collide simultaneously to form the products. Yeah, that defines the molecularity of the reaction. If I'm saying molecularity of the reaction is 0, that means no reacting species are colliding. If the reacting species are not colliding as per collision theory, the reaction is not going to happen. So molecularity of the reaction can never be 0. It can never be fractional. I can never say 1.5 molecules have collided simultaneously and formed the product. No, I cannot say that. Yeah, molecularity can never be negative, right? I cannot say -3 molecules have collided and formed the products, right? Which does not have any significance at all. So remember, molecularity of the reaction, it can never be 0, it can never be fractional, and it can never be negative at the same time. Yeah, and people remember, this is again one important point. Reactions with molecularity greater than 3, they are rarely found. They are rarely observed. What is the reason for that? Reactions which have got molecularity greater than 3, those are rarely found. Yeah. See, let's say I've got a reaction in which two reacted molecules are colliding simultaneously and forming the product. So I can clearly say molecularity of this reaction is 2. Now I have got, for example, 3 reacting molecules like this, okay? They are colliding simultaneously and forming the product. So I'll clearly say molecularity of this reaction is 3, right? Now reactions with molecularity greater than 3, those are rarely found because the probability of more than 3 molecules, to collide simultaneously, that's very less. If the probability of more than 3 molecules to collide simultaneously is very less, I can clearly say reactions with molecularity greater than 3, those are rarely found, right? Those are rarely observed, correct? Yes, as simple as that. Now people, molecularity, remember, it's only defined for elementary reactions, it's not defined for complex reactions. Molecularity for the complex reaction has actually no physical significance, yeah? Molecularity term, it's used for the elementary reactions only. Remember this as well. These are the 3 important points. Molecularity can never be 0, fractional or negative. Reactions with molecularity greater than 3 are rarely observed, and molecularity is only defined for the elementary reactions, yeah? Okay. Now people, look here, understand properly. In a complex reaction, each step has its individual molecularity, right? As I told you, see, first of all, if I'll be adding these 2 reactions right here, what is the net reaction which I'll get? NO plus NO, that becomes 2 times NO plus Br2. It gives 2 times NOBr, right? This is the net reaction which I'm getting after adding the first 2 reactions. So I'm calling this reaction as the complex reaction. I'm calling this reaction as a complex reaction, right? Yes, right? Now people understand. These are the steps which are involved in this complex reaction. And the steps involved in the complex reactions are always elementary. So this is elementary, this is again elementary. And molecularity is only defined for elementary reactions. So this step is elementary, this step is elementary. So I can define molecularity for this reaction. Molecularity for this reaction is going to be 1 plus 1, 2. Molecularity of this reaction is going to be again 1 plus 1, 2, right? I cannot calculate the molecularity of this complex reaction, which does not have any physical significance because molecularity is only defined for the elementary reactions, yeah? Now there is one important topic, that's what they call as order of the reaction, yeah? Right? What is this order of the reaction all about? Let's get to know that, yeah? So first of all, you let me know in the chat box if everything is clear till here or not. Let me know in the chat box. Let me know in the chat box if everything is clear till here. No, Pravishni, you cannot say that. You cannot say that. Let me know first if it is clear to everyone so that I can move on. Let me know in the chat box first, yeah? Okay, and people, do not forget to like the video, do not forget to share the video with your friends, and do not forget to subscribe to the channel as well, right? Yes, Rajaraman, I'll be doing the rank booster series for 2021 students. That is tomorrow. Tomorrow I'm taking a rank booster session for the JEE 2021 students at the same time, 10:30 p.m. Yeah. Okay, let's move on. Let's go to the actual stuff. That's something called as order of the reaction. How do we define the order of the reaction? That's important. Understand what I'm going to say. Well, people, the sum of the powers of all the concentration terms, involved in the rate expression is what I call as order of the reaction. What is meant by that? See, let's assume this is a balanced chemical equation which I have. Let's assume this is in aqueous form. This B is also in aqueous form. Okay. If I'll be writing the rate law for this reaction. Remember, whenever I try to calculate the order of the reaction, I always write the rate law for the reaction first. So rate law of the reaction is going to be R is equal to K multiplied by concentration of A raised power X multiplied by concentration of B raised power Y. Yeah? Okay. Right? As simple as that. Remember, whenever I need to calculate the order of the reaction, I'll be writing the rate law first for the reaction. Okay? After writing the rate law, what is the power of this term? Power of this term is X. What is the power of this term? Power of this term is Y. This X is something which I'll be calling as order of the reaction with respect to A. Order of the reaction with respect to A. And this Y is what I call as order of the reaction. Order of the reaction with respect to B. With respect to B, right? And if I'll take the sum of these powers, if I'm simply doing as X plus Y is what we call as overall order of the reaction. It's what we call as overall order of the reaction. Okay. Now, what is the significance of this order? This is something you'll get the idea of in some time. Okay. But remember, whenever I need to calculate the order of the reaction, right? Whenever I need to calculate the order of the reaction, I'm supposed to write the rate law first. After writing the rate law, whatever will be the powers of these concentration terms, this X and Y, if I take sum of these powers gives me basically the order of the reaction. Yeah? Okay, as simple as that, right? Now, people, since in order to calculate the order of the reaction, we need to write the rate law, and rate law is something which is experimentally determined. That means the order of the reaction will be also experimentally determined, right? Order of the reaction is also experimentally determined quantity, right? Remember, order of the reaction, it can be 0, positive or fractional as well. Unlike your molecularity, molecularity can never be 0, molecularity can never be fractional, right? But order can be 0, order can be fractional, right? Any reaction which will be having the overall order as 0, we call that reaction as the 0 order reaction. Any reaction which has got the overall order as 1, we call that reaction as the first order reaction. Any reaction which has got the order as fraction, like 1 by 2, something like that, yeah? Okay, we call that reaction simply as the fractional order reaction. Now, what is important? Have a look. Order of the reaction can be negative with respect of any of the reactants, but remember, overall order of the reaction can never be negative. Remember, overall order of the reaction can never be negative. What it means? Let's say I've got the reaction as N1A plus N2B. It gives products. Let's assume this is the reaction which I have. Yeah. Let's assume the rate constant of this reaction is K. This is the rate constant of the reaction which I'm assuming. Yeah. Now, in order to calculate the order, I need to write the rate law. R is equal to K multiplied by concentration of A. Since I'm writing rate law, so I'll be writing X multiplied by concentration of B. I'll be writing Y over here, right? This X is what I call as order of reaction with respect to A. Y is what I call as order of reaction with respect to B. Remember, X can be negative. X can be negative. Y can be negative. But remember, X plus Y, it can never be negative. That's why I'm writing over here order of the reaction with respect to any of the reactants. That means X or Y. X can be negative, Y can be negative, but overall order X plus Y can never be negative. Remember this thing as well, which is very important, yeah? Now comes one more important statement. For the elementary reaction, order is always equal to molecularity, right? if I'll be having any elementary reaction which gets completed in a single step, for that reaction, its order is always equal to its molecularity. How can we understand this statement? Have a look. Let's say I've got the reaction as 2A plus B, it gives products. Let's assume this is the reaction which I have, okay? Let's assume rate constant of this reaction is K, and I'm assuming it is an elementary reaction. I'm assuming it's an elementary reaction, yeah? As we already know, for elementary reaction, law of mass section is truly valid, right? Okay, if I want to write the rate law for this reaction, but before writing the rate law, if I'll ask you, since it's an elementary reaction, molecularity is defined for elementary reactions only. If I'll ask you what is the molecularity of this reaction, you'll say two molecules of A are simultaneously colliding with one molecule of B and product is getting formed. So molecularity of this reaction is 3, right? Molecularity of this reaction is 3, correct? Okay. Now people, if I want to write the rate law for this reaction, R is going to be equal to K multiplied by concentration of A raised power X multiplied by concentration of B raised power Y. This is the rate law of the reaction. But for elementary reactions, I have told you, these powers are basically the stoichiometry coefficients, because for elementary reactions, experimentally determined rate is always equal to the theoretically determined rate, okay? So I can write rate of the reaction directly as K multiplied by concentration of A. Instead of X, I'll be writing the stoichiometry coefficient 2. Instead of Y, I'll be writing the stoichiometry coefficient 1, yeah? Okay. This 2 is the order of reaction with respect to A, 1 is the order of reaction with respect to B. So what is the overall order of the reaction? Overall order of the reaction is equal to X plus Y, 2 plus 1, that comes out to be 3. So I can say for the elementary reaction, order is equal to its molecularity. Order of elementary reaction is always equal to its molecularity. Right? Mr. Dharma, you can look at the name of the channel. It's an English channel, okay? Right? I hope you get it. People, let me know if it is clear to everyone or not. Let me know if it's clear till here or not. Fast. Let me know fast in the chat box if it's clear to you or not. Order of the reaction is equal to the molecularity of the reaction, provided the reaction is elementary. Okay? Yeah? Let's assume I've got the reaction as simple. A plus B gives products. Let's assume this is the elementary reaction. Can you let me know in the chat box what is the order of the reaction? Can you let me know in the chat box what is the order? Can you let me know what is the overall order of the reaction? Fast. Can you let me know what is the overall order of the reaction? Absolutely, it's going to be 2, right? Because for the elementary reaction, order is equal to molecularity. So molecularity is 1 plus 1, 2. So order of the reaction will be also 2, right? As simple as that. This was important, correct? Now people, can you let me know which statement is absolutely correct among the two? Can you let me know which statement is absolutely correct among the two, right? A unimolecular reaction must be first order. Second point says a unimolecular elementary reaction must be first order. Which statement is correct among the two? What do you think? Which statement is correct among the two? What do you think? A unimolecular reaction must be first order. Second is a unimolecular elementary reaction must be of first order. It is the second statement actually which is true. It is the second statement which is true. Why is that? See, look at the first one. A unimolecular reaction, that means that reaction whose molecularity is 1. Okay, a unimolecular reaction must be of the first order. That means if I'll be having any unimolecular reaction whose molecularity is 1, its order should be also 1. But molecularity is equal to order only in case of elementary reactions. Not in case of complex reactions. So first statement is not valid at all. But the second statement, a unimolecular elementary reaction whose molecularity is 1, okay? Unimolecular elementary reaction must be of first order, right? If I'll be having a unimolecular reaction which is elementary in nature, that means its order should be equal to its molecularity, right? So a unimolecular elementary reaction must be of the first order. This is the correct one. First one is not correct, right? Correct? A unimolecular reaction must be first order. It is not correct. Unimolecular reaction can be complex as well, yeah? Okay? So the correct statement is a unimolecular elementary reaction must be of the order 1. Because for the elementary reactions, order is equal to molecularity. If I'll be having the reaction whose molecularity 1, its order can be only equal to 1 if it is elementary in nature. I'm sure it's clear to everyone, right? There is one more statement. Can you let me know is the statement correct or not? A zero order reaction must be complex. Can you let me know in the chat box is this correct or not? A zero order reaction must be complex. What do you think? What do you think? A zero order reaction must be complex. What do you think? A zero order reaction must be complex. What do you think? Is it true? Absolutely, it is true. Why is that? See, a zero order reaction can never be elementary. Can never be elementary. Why is that? If I'll be having a zero order reaction, that means if I'll be having a reaction whose order is 0, okay? If the zero order reaction will be elementary, right? That means its molecularity should be also 0. If the zero order reaction will be elementary, that means its molecularity should be also 0. But reaction with molecularity 0, does that make any significance? No. So remember, a zero order reaction can never be elementary. If the zero order reaction was elementary, then the molecularity of the same reaction should have been 0. But the molecularity of the reaction can never be 0, okay? So zero order reaction, it can never be elementary, it's always complex, yeah? Okay, I'm sure it's clear till here, right? Now comes a term, a relation between different rate constants. Relation between different rate constants, okay? Understand this thing as well. This is very important. This is very important. First of all, I'm given with a balanced chemical equation. If I'll try to write the differential form of rate, the differential form of rate is going to be equal to, I'll start with a minus sign, 1 divided by stoichiometric coefficient of A, change in the concentration of A divided by dt, right? This is the rate of reaction with respect to A. Same, I can write the rate of reaction with respect to B as well, minus 1 divided by N2. It is going to be change in the concentration of B divided by dt. It can be equal to plus 1 divided by N3, change in the concentration of C divided by dt, which can be also equal to plus 1 divided by N4, change in the concentration of D divided by dt, right? If I'll take any one of these terms right here, that's simply going to give me the rate of the reaction, right? If I'll take this term, I can calculate rate of reaction. If I'll take this term out, rate of reaction. If I'll take this term out, that will give me the rate of reaction. If I'll take this term out, that's actually going to give me the rate of reaction. And at the same time, if I'll write the rate law for the same reaction, if I write the rate law for this reaction, I can say rate of reaction is equal to rate constant multiplied by A key concentration raised power, for example, X multiplied by B key concentration raised power Y. This is the rate law which I have written for the given reaction. Since this rate law is giving me the rate of reaction and all these terms are again giving me the rate of reaction, right? And rate of the reaction at a particular temperature that has a fixed value. So whatever rate of reaction you'll be getting by solving this equation, same value of rate of reaction you'll be getting by solving this equation, okay? So I can directly equate these two terms. I can write minus 1 divided by N1 d of A divided by dt is equal to K multiplied by A key concentration raised power X multiplied by B key concentration raised power Y. What is K? K is the rate constant of the reaction. K is the rate constant of the reaction, correct? Now people understand. I can write it like this as well. Minus d of A divided by dt is equal to N1 multiplied by rate constant of the reaction multiplied by A key concentration raised power X multiplied by B key concentration raised power Y, right? Okay. Yeah, I'm sure it's clear to everyone. What is this minus dA by dt? Minus dA by dt, it is something which I call as the rate of disappearance of A. Rate of disappearance of A, correct? Right? Now we will see this N1 multiplied by K. This N1 multiplied by K. Since N1 is a constant, K is a constant, N1 multiplied by K, product of two constants is always a new constant, and this new constant is represented by Ka. What is this Ka? Ka is what we call as the rate constant of disappearance of A. Rate constant of disappearance of A. And this K is what we call as the rate constant of the reaction. This is the overall rate constant of the reaction, right? This K is the overall rate constant of the reaction. This K is the rate constant of disappearance of A. Okay, I got one important result from here. I got to know rate constant of the reaction multiplied by stoichiometric coefficient of any of the reactant. It always gives me the rate constant of disappearance of the reactant. Okay, what does it mean exactly? Have a look. I got something as, see, I'm writing something as Ka. Ka is what we call as the rate constant of disappearance of A. It will be equal to N1 multiplied by rate constant of the reaction. Similarly, if I write Kb, Kb will be equal to N2 stoichiometric coefficient of B multiplied by rate constant of the reaction. If I write Kc, Kc will be equal to N3 multiplied by rate constant of the reaction, right? If I write Kd, Kd will be equal to N4 multiplied by rate constant of the reaction. What is Ka? Ka is the rate constant of disappearance of A. Kb is the rate constant of disappearance of B. Kc is the rate constant of the appearance of C, and Kd is the rate constant for the appearance of D, right? So remember, in general, rate constant of appearance or disappearance is always equal to stoichiometric coefficient multiplied by overall rate constant of the reaction. Why am I telling you all this? Because there's a reason for that. This is the simplest question which I want you guys to do right now. See guys, the question says, I'm given with the reaction. The reaction says 2A plus, the reaction is 2A plus 3B gives C, right? 2A plus 3B gives C. The rate constant of the reaction I'm representing by K reaction, okay? Find the relation, as per the question, find the relation between K1, K2 and K3. K1 is the rate constant of disappearance of A, K2 is the rate constant of disappearance of B, K3 is the rate constant of appearance of C. So I'm writing K1. Rate constant of disappearance of A will be equal to rate constant of the reaction multiplied by stoichiometric coefficient of A, that is 2. Similarly, if I write K2, rate constant of the reaction multiplied by stoichiometric coefficient of B. Similarly, if I write K3, K3 is the rate constant of rate constant of appearance of C, which is going to be equal to rate constant of the reaction multiplied by stoichiometric coefficient of C. So from the first equation, can I get the value of K? K is simply going to be equal to K1 divided by 2. From the second equation, can I get the value of K, which is simply going to be equal to K2 divided by 3. From the third equation, I can get the value of K, which is simply going to be equal to K3. Okay? See, so I got to know K is equal to K1 by 2, K is equal to K2 by 3, K is equal to K3, right? If I compare all these three, I can clearly say K1 divided by 2 is equal to K2 divided by 3, which is equal to K3, right? If I take the LCM of denominators, that is 6, just multiply this term by 6, just multiply this term by 6, just multiply this term by 6. So the value comes out to be 3 times K1, 2 times K2 is equal to 6 times K3. This is the relation between K1, K2 and K3, right? Yeah? Right? Let me know in the chat box if it's clear. Fast. Let me know in the chat box if it's clear. Fast, right? Right? Let me know in the chat box if everything is clear till here or not. Yeah? Perfect. Perfect, guys. Perfect. Okay. So let's talk about something called as units of rate constant. Let's talk about something called as units of rate constant, okay? How do we write the units of rate constant? For example, I've got the reaction as N1A gives N2B. Let's assume this is the reaction. Its order is K. Sorry, its rate constant is K. Let's assume order of the reaction is equal to N. It is an nth order reaction. N can be 0, 1, 2, whatever, yeah? First of all, if I write the rate law is going to be equal to K multiplied by concentration of reactant A raised by X. X will be the order of reaction with respect to A, and X will be the overall order of the reaction as well. But overall order of the reaction is N, so it's A raised by N, correct? So I can say K will be equal to R divided by concentration of A raised by order, correct? And people, if this A is in gaseous phase, if this A and B is in gaseous phase, I can write the rate law like this as well. R is equal to K. Instead of concentration of A, I'll be writing pressure of A raised by raised by the order, that's N. So from here you can calculate the K value. It's going to be R divided by pressure of A raised by order, that is N, correct? Now, the units of K over here will be equal to rate Over here we'll have the units, moles, liter inverse divided by moles, liter inverse, second inverse. Concentration has got the unit as mole liter inverse, but it is raised par n. So the overall unit of rate constant in general is going to be mole liter inverse raised par 1 minus n and then second inverse. Over here you've got mole liter inverse, mole liter inverse. Bases are same, powers are subtracted in case of division, right? Right? Okay. Now people are the same. See, this is one of the general units of rate constant, right? One more general unit of rate constant is going to be, see, over here I've got rate. Rate has got the unit as ATM, second inverse as well, divided by. In the denominator we have got pressure. Pressure has got the unit ATM raised par order. So it's going to be ATM raised par 1 minus n and second inverse. These are the general units of rate constant over here. So rate constant units is going to be either this or it's going to be this one, right? Now, depending on whether you have got the zero order, first order reaction, okay, and so on, you can put the value of n and get the value of rate constants. For example, I've got a zero order reaction. Let's assume I've got a zero order reaction. Zero order reaction means n key value is 0. If n value is 0, then rate constant will have got the units. If n value is 0, n value is 0. So it's going to be moles, liter inverse or second inverse, or in terms of pressure, it's going to be ATM second inverse. As simple as that, right? These are the units of rate constant for a zero order reaction. Similarly, for a first order reaction, you can put the value of n as 1. So it's going to be mole liter inverse raised par 1 minus 1. 1 minus 1 is 0. Anything raised par 0 is 1. So for a first order reaction whose n value is 1, rate constant will have got the unit simply as second inverse from here as well, from here as well. Yeah, very simple, correct? Now, what is the significance of the order of the reaction? What all things can we depict from the order of the reaction? Well, people, order of the reaction simply gives us the idea about how many times rate of reaction changes on changing the concentration of reactant. On changing the concentration of reactant. If I'll change the concentration of reactant, how many times rate of reaction changes? Okay, that's something which is given by the order of the reaction. For example, see, if this is the elementary reaction, so its law of mass action will be equal to its rate law, right? I can write the rate law directly as R is equal to K, A ka power, that's 1, B raised par 2. Because for elementary reaction, rate law is equal to law of mass action, correct? Right? Now we will understand. What is this 1? 1 is the order of reaction with respect to A, 2 is the order of reaction with respect to B, correct? People, if I keep the concentration of B fixed, if I do not let the concentration of B to change, and at the same time, if I'm keeping the concentration of B as fixed, I'm just doubling the concentration of A. If I'll double the concentration of A, rate will also double, right? If I make the concentration of A 3 times, rate will also become 3 times. If I'll make the concentration of A 4 times, rate will also be 4 times, right? So can I say rate of reaction varies linearly with the power of A, right? Rate of reaction varies linearly with the power of A, correct? Similarly, if I keep the concentration of A fixed, constant, and I'm doubling the concentration of B, I'm making the concentration of B 2 times, and the power is 2. If I make the concentration of B 2 times, the rate will be 4 times. If I make the concentration of B 3 times, rate will be 9 times. If I make the concentration of B 4 times, rate will be 16 times. So can I say order of the reaction is giving me the idea about how many times the rate of reaction changes on changing the concentration of reactants. As simple as that, yeah? Right? Now people, there are few questions which we can solve right here. Very simple, okay? I'm sure all of you can solve this question. I'm sure about it. For a chemical reaction, A gives B. Well, I'm given with a chemical reaction, and the chemical reaction is A gives B. Okay? The rate constant of the reaction is K. It is found that a rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. The reaction which we have right here, let's assume the order of this reaction is equal to n. Let's assume it is the nth order reaction. Order of the reaction is equal to n. First of all, I can write the rate law for this reaction. It's going to be equal to K multiplied by concentration of A raised per order, that's n, right? Because whenever I need to calculate order, I always need to write the rate law. I have written the rate law. Let's keep this equation number 1, okay? Now, it's mentioned in the question, it is found that the rate doubles. The rate doubles. Initially it was R, now it is 2R. The rate doubles when the concentration of A is increased 4 times. Initially it was A, now it becomes 4 times A. Right? Let's keep this equation number second, correct? If I divide the two equations, second divide by first. If I divide the two equations, second divide by first, RR gets cancelled, so it becomes 2, KK gets cancelled, A raised power n, A raised power h gets cancelled, so it becomes simply 4 raised power n, right? So can I say 2 is equal to 4, I can write 2 square raised power n, correct? Or it's simply going to be 2 is equal to 2 raised power n, right? When can be this equation true? This equation can be only true if 2n value is equal to 1. If 2n value is equal to 1, which simply says n value is equal to 1 by 2. What is n? N was the order of the reaction. So I got to know the reaction is fractional order, right? The order of the reaction is 1 by 2, yeah? Right? Author, then you cannot say it. Yeah, then you cannot say it. Okay? Right? As simple as that. Now people, there is one question which I'm giving you as the homework. This is the question which I'm giving you as the homework. Do let me know answer of this question in the comment section, right? Do write the answer of this question in the comment section once the session ends, right? I believe this was the last question, right? And with this, I end the session. But before ending the session, let me give you the quick overview of the next batch for class 12, which is starting on 14th of June, okay? On 14th of June, we are starting a batch on actual Vedantu platform, and these are the 3 plans for you. These are the 3 plans for you. You can take any of these plans. Well, this is the course fee for 12 months for the entire 1-year program, and you can pay this much of amount in installments as well. If you are taking light plan, you have to pay this much of amount, but you can pay this much of amount in installments as well. Similarly, if you are taking the second plan, you have to pay this much of amount. This is the course fee for 12 months, you can pay this much of amount in installments as well. Similarly, this one you can pay installments, right? But if you are new to Vedantu, you have no idea of how the actual Vedantu platform looks like, how the actual classrooms of Vedantu are, you can just take these pro subscription on trial basis as well. You can take this pro subscription for a month. For a month, you have to pay this much of amount, okay? And for a month, you can sit in the batch. If you think you are getting benefited, then go for the 1-year classroom program, right? Similarly, if you want to take this program over here, you can give it a try for a month, right? Then go for the 1 year. Similarly, get the trial for a month and go for the 1-year program, right? If you are new to Vedantu. And while enrolling, do one thing. Do not forget to use this coupon code WSPRO. It's my personal coupon code, Wassim Sir's Pro subscription. On using this coupon code, you'll be getting some additional discount and you'll be directly getting enrolled in my personal batches, okay? Do not forget to use this coupon code while enrolling. And the link is there in the description box of the video. Click on the link, use the coupon code WSPRO and get the additional discount of almost 20%, yeah? There is one more link in the description box, that's for the Telegram. Do click on the link, get added to the Telegram group and stay updated about the classes. And the ones who have not liked the video yet, please do like the video, share the video with your friends and do not forget to subscribe to the channel as well, yeah? Okay. Well, Shankar, you can get the pro subscription and then talk to the operational team. You'll be getting in, okay? So, Bill, it was nice meeting you. I'll see you guys tomorrow at the same time. The question which I gave you as the homework, do let me know the answer of this question in the comment section, yeah? Now, I'll see you guys tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.